Welcome, everyone. Today we are diving into the fascinating world of period 3 elements. We are going to explore how their physical and chemical properties change as we move across the periodic table from left to right. Let's start by looking at some raw data. As we move from sodium to argon, we transition from metals to a metalloid and finally to nonmetals. Notice how the bonding changes from metallic to covalent, and the structures shift from giant metallic lattices to a giant covalent network, and eventually to simple molecules. These structural shifts are the key to understanding the drastic changes in melting and boiling points. Why do we see this shift from metals to nonmetals? It all comes down to how strongly these atoms hold onto their electrons. On the left side, elements like sodium have low ionization energies and low electronegativity, meaning they easily lose electrons to form metallic bonds. As we move right, electronegativity increases, meaning atoms hold electrons more tightly, leading to nonmetallic covalent behavior. Next, let's look at the size of these atoms. If you measure the atomic radius, you will find a clear trend. The atoms get progressively smaller as we move from sodium across to argon. But why would they get smaller if we are adding more protons and electrons? The answer lies in the concept of effective nuclear charge. As we move across period 3, we are adding electrons to the exact same energy shell. This means the inner shielding or screening effect barely increases. However, we are also adding protons to the nucleus. This increasing positive charge pulls that same outer shell of electrons closer and closer, shrinking the overall radius of the atom. Now, let's talk about conductivity. Metals like sodium, magnesium, and aluminium are excellent conductors of both heat and electricity, and this conductivity actually increases from sodium to aluminium. Nonmetals, on the other hand, are insulators. They hold their electrons tightly in localized covalent bonds, so there are no free charges to carry a current. The secret to metallic conductivity is the sea of delocalized electrons. Sodium contributes 1 valence electron per atom to this free-flowing cloud, magnesium contributes 2, and aluminium contributes even more. More free electrons mean better conductivity. Silicon, sitting in the middle, is a metalloid. Its electrons are in covalent bonds, but it takes less energy to free them than in true nonmetals, making it a semiconductor. Let's apply this to a real-world scenario. Imagine a student named Amina testing materials at a science fair. She finds that aluminum foil lights up a circuit, but red phosphorus does not. As we just discussed, aluminum's giant metallic structure provides a mobile cloud of delocalized electrons to carry the current. Phosphorus, however, is a simple molecular nonmetal where all valence electrons are locked tightly in covalent bonds, leaving nothing to conduct the electricity. Moving on to melting and boiling points, we see a very distinct mountain-shaped trend. The melting points rise steadily from sodium to aluminum, peak dramatically at silicon, and then plummet to very low values for phosphorus, sulfur, chlorine, and argon. Let's break down exactly why this happens, starting with the metals. For the metals, melting requires breaking strong metallic bonds. As we move from sodium to magnesium, the atoms get smaller and contribute more electrons to the delocalized sea, making the metallic bond much stronger and the melting point higher. Interestingly, aluminum's melting point is only slightly higher than magnesium's. This is because the highly charged aluminum ion doesn't fully release all 3 of its valence electrons into the metallic bond. Then we hit silicon, which has the highest melting point of the entire period. Silicon doesn't form metallic bonds. Instead, it forms a giant covalent structure. Every single silicon atom is bonded to 4 others in a massive, infinite 3D tetrahedral network. Because silicon atoms are relatively small, these covalent bonds are short and incredibly strong. Melting silicon means breaking millions of actual chemical bonds, which requires a massive amount of thermal energy. After silicon, the structure changes drastically. Phosphorus, sulfur, and argon exist as simple molecules. Within the molecules, the atoms are held by strong covalent bonds, but between the molecules, there are only weak van der Waals forces. When you melt these elements, you only need to overcome these weak intermolecular forces, not the covalent bonds. This is why their melting points drop so significantly. Even among the nonmetals, there is a mini-trend based on the size of the molecules. The strength of van der Waals forces increases with molecular mass. Sulfur exists as a large 8-atom ring, S8, giving it the highest mass and the highest melting point of this group. Phosphorus forms P4 molecules. Chlorine forms diatomic Cl2, and argon exists as single spherical atoms. As the molecules get smaller, the intermolecular forces get weaker. Visualizing these structures helps make sense of the data. You can see the infinite network of silicon compared to the discrete molecules of the nonmetals. The bulky S8 ring of sulfur has a lot of surface area for van der Waals forces to act upon, which is why it requires more energy to melt than the smaller P4 tetrahedron of phosphorus or the simple Cl2 molecule. Let's put on our engineering hats. If you need a material to withstand high temperatures, you would look at this data and immediately rule out sodium and phosphorus. You would explain to the engineer that the giant covalent network of silicon provides the ultimate thermal stability, followed by the strong metallic lattices of aluminum and magnesium. Understanding the underlying bonding is crucial for practical applications. In a similar laboratory scenario, students comparing the nonmetals would note that argon melts at a freezing negative 159 degrees Celsius. You could explain to them that because argon is monoatomic and perfectly spherical, the contact area between atoms is minimal. This results in the weakest possible van der Waals forces, making it a gas at room temperature, unlike the larger, heavier sulfur and phosphorus molecules. We have thoroughly explored the physical properties of period 3, from atomic radius to melting points, and seen how structure dictates behavior. But how do these structural differences affect how these elements react with the world around them? Next, we will dive into their chemical properties, starting with how they interact with air and water. Moving right along, let's examine the general reactivity trends across period 3. For the metals, sodium, magnesium, and aluminum, reactivity actually decreases across the period. Why? Because atomic radius decreases, causing an increase in ionization energy and a drop in electropositivity. The nucleus holds on to those valent electrons much more tightly, making it harder for them to be lost to form positive ions. Conversely, when we look at the nonmetals from silicon to chlorine, their reactivity increases across the period. As the atomic radius continues to shrink, electronegativity and electron affinity increase. The nucleus exerts a stronger pull, which makes it much easier for these atoms to gain incoming electrons and form negatively charged ions. Let's see how these elements react with air, specifically oxygen. Sodium is highly reactive. When heated in oxygen, it burns with a bright orange flame. If oxygen is limited, it forms a white powder of normal sodium oxide. But in an excess supply of oxygen, it produces a yellow solid known as sodium peroxide. Magnesium burns with a blinding, intense white flame to form white magnesium oxide. Interestingly, if burned in normal air, the massive heat released is enough to break the strong triple bonds of nitrogen gas, forming magnesium nitride as well. If you add water to this magnesium nitride, it hydrolyzes to release ammonia gas. Magnesium's combustion is so energetic that it will even continue to burn in a stream of carbon dioxide. The heat decomposes the carbon dioxide, stripping the oxygen to form magnesium oxide and leaving behind specks of black carbon. If you heat magnesium in a glass tube, it will even react with the glass itself, extracting silicon and boron to leave dark gray residues. Moving to aluminum, bulk aluminum has a tough protective oxide layer that inhibits reaction. But if you sprinkle aluminum powder into a flame, it burns with brilliant white sparkles to form aluminum oxide. Silicon is less reactive. It requires very strong heating and oxygen to finally ignite and form silicon dioxide. Phosphorus presents an interesting case. White phosphorus is so reactive it catches fire spontaneously in air, burning with a white flame and producing thick white smoke. Depending on the oxygen available, it forms either phosphorus 3 oxide or, in excess oxygen, phosphorus 5 oxide. These oxides typically dimerize in the gaseous state. Sulfur requires gentle heating to burn, producing a pale blue flame and colorless, pungent sulfur dioxide gas. To push this further to sulfur trioxide, you need a vanadium 5 oxide catalyst and high pressure. Finally, chlorine and argon do not react directly with oxygen at all. Now let's look at reactions with water. The reactivity drops as the metal hydroxides become less soluble. Sodium reacts violently with cold water, melting into a silvery ball and releasing hydrogen gas. Magnesium barely reacts with cold water because an insoluble layer of magnesium hydroxide stops the reaction. But if you expose magnesium to hot steam, it reacts vigorously to form magnesium oxide and hydrogen. Aluminum doesn't react with cold water at all due to its protective oxide layer. However, if heated with steam, that layer is partially removed, allowing it to react moderately to form aluminum oxide and hydrogen. Silicon is even more stubborn. Standard, shiny silicon lumps only react with steam at red heat to produce silicon dioxide and hydrogen gas. White phosphorus ignores cold water entirely, but when vaporized and heated with steam, It reacts slightly to form phosphorus-3 oxide and hydrogen gas. Sulfur, on the other hand, is completely unreactive with both cold water and steam. Chlorine slowly and partially dissolves in cold water to form a light green solution. This is a reversible reaction that yields a mixture of hydrochloric acid and chloric-1 acid, also known as hypochlorous acid. If left in sunlight, the chloric-1 acid decomposes, shifting the reaction to produce more hydrochloric acid and releasing oxygen gas. Argon, being a noble gas, does not react with water. Moving on to reactions with strong alkalis like sodium hydroxide. Sodium and magnesium don't react because they are highly electropositive and basic themselves. Aluminum, however, is amphoteric. It dissolves in hot dilute sodium hydroxide to form a tetrahydroxyl aluminate complex, and in hot concentrated alkali, it forms anhydrous sodium dioxoaluminate, releasing hydrogen gas in both cases. You might wonder why aluminum forms these complex ions. It's because the aluminum ion has a very high charge density. It has a small ionic radius, but a high +3 charge. This strongly attracts ligands, which are molecules or negative ions with lone pairs of electrons, allowing them to form coordinate or dative bonds with the empty d orbitals of the aluminum cation. Nonmetals also react with hot, concentrated alkalis to form oxoanions. Silicon reacts to form sodium silicate and hydrogen gas. White phosphorus reacts to produce sodium phosphonate alongside phosphine gas. Sulfur undergoes a disproportionation reaction in sodium hydroxide, forming a mixture of sodium sulfide and sodium sulfite along with water. Chlorine's reaction with sodium hydroxide depends heavily on the conditions. In cold, dilute alkali, it forms sodium chloride and sodium chlorate 1. But if you use hot, concentrated sodium hydroxide, the reaction goes further to produce sodium chlorate 5 along with sodium chloride. Chlorine is much more soluble in alkalis than in water because the hydroxide ions neutralize the acidic products, driving the equilibrium forward. Next, let's observe how these elements react with dilute acids. Sodium reacts violently and magnesium moderately to form salts and hydrogen gas. Note that nitric acid usually doesn't liberate hydrogen because it's a strong oxidizing agent. However, magnesium is one of the rare exceptions that will react with very dilute nitric acid to produce a small amount of hydrogen gas. Aluminum reacts slowly with hot dilute hydrochloric or sulfuric acid to form salts and hydrogen. If you use hot concentrated sulfuric acid, the acid acts as an oxidizing agent, reducing itself to sulfur dioxide gas instead of hydrogen. Interestingly, hot concentrated nitric acid doesn't dissolve aluminum. Instead, it rapidly forms a thick, impervious oxide layer that renders the metal completely passive. For the nonmetals, sulfur is oxidized by hot concentrated sulfuric acid to sulfur dioxide, and by hot concentrated nitric acid all the way to sulfuric acid, releasing nitrogen dioxide. Silicon, phosphorus, and chlorine generally don't react with standard acids because they are acidic themselves. The only exception is silicon reacting with hydrofluoric acid to form a soluble hexafluorosilicate complex ion. Finally, let's look at reactions with chlorine gas. The metals react vigorously when heated. Sodium burns with an orange flame to form sodium chloride, and magnesium burns with a white flame to form magnesium chloride. Aluminum burns in a stream of dry chlorine to produce aluminum chloride, a fascinating compound that sublimes into a vapor where it dimerizes into Al2Cl6 before condensing back into a solid. The nonmetals also form chlorides. Silicon reacts with chlorine to produce silicon tetrachloride, a colorless liquid. Phosphorus can form two different chlorides. With limited chlorine, it forms liquid phosphorus trichloride, and with excess chlorine, it forms solid phosphorus pentachloride. Sulfur reacts to form an orange, foul-smelling liquid called disulfur dichloride. We will explore the specific properties of these period 3 compounds in the next segment. Moving right into the compounds of period 3 elements, let's first examine their oxides. As we look across the period from sodium to chlorine, we see a distinct shift in physical properties. The melting and boiling points start high with sodium and magnesium oxides, peak at magnesium oxide, and then generally decrease as we move towards sulfur and chlorine oxides. This macroscopic trend is a direct result of the shifting bonding and structural types, from giant ionic lattices on the left to a giant covalent network for silicon dioxide, and finally to simple molecular structures held together by weak van der Waals forces on the right. Let's break down exactly why we see this variation in melting and boiling points. Sodium, magnesium, and aluminum oxides form giant ionic structures. Their oppositely charged ions are locked together by strong electrostatic forces, requiring massive amounts of energy to break. The strength of these ionic bonds actually increases from sodium oxide to magnesium oxide because the magnesium cation is smaller and has a higher charge, meaning the ions attract each other much more slowly. However, aluminum oxide breaks the pattern slightly. It has a lower melting point than magnesium oxide because the highly charged aluminum ion polarizes the oxygen ion, introducing a covalent character that slightly weakens the overall ionic lattice. Silicon dioxide presents a different case. It exists as a giant covalent structure. Instead of an ionic lattice, the atoms are held together by a vast network of short, strong covalent bonds. While these individual bonds are strong, the overall network requires less heat energy to break apart compared to the strongest ionic bonds, which is why silicon dioxide has a lower boiling point than aluminum oxide. Structurally, every single silicon atom is covalently bonded to 4 oxygen atoms, creating an infinite three-dimensional tetrahedral network. Beyond physical states, the chemical nature of these oxides changes drastically across the period. We transition from strongly basic oxides on the left, like sodium and magnesium oxide, to an amphoteric oxide in the middle, with aluminum oxide, and finally to strongly acidic oxides on the right, with silicon, phosphorus, sulfur, and chlorine. This chemical shift perfectly mirrors the transition from metallic to non-metallic character across the periodic table. Additionally, the ionic oxides on the left exhibit high electrical conductance when molten or dissolved in water, a property absent in the covalent oxides on the right. How do we actually prepare these metal oxides in the lab? For sodium, burning it in a limited supply of oxygen yields sodium oxide, but an excess of oxygen produces sodium peroxide. Magnesium oxide can be formed by directly heating magnesium in air, reacting it with steam to release hydrogen gas, or by thermally decomposing magnesium carbonate, nitrate, or hydroxide. Similarly, aluminum oxide is prepared by heating aluminum in dry oxygen or steam, or by decomposing aluminum hydroxide or aluminum nitrate. For the nonmetals, direct combination with oxygen is also a primary method. Silicon dioxide is formed by heating silicon and dry oxygen, or by combusting saline. Phosphorus is quite reactive. Burning white or red phosphorus in a limited supply of oxygen yields phosphorus 3 oxide, whereas an excess of oxygen pushes the reaction further to form phosphorus 5 oxide. Sulfur burns in a stream of dry oxygen to form sulfur dioxide. To get sulfur trioxide, we must use excess oxygen, high pressure, and a vanadium 5 oxide catalyst to drive the reversible reaction forward. When we drop these oxides into water, their basic or acidic nature becomes very apparent. Sodium oxide and sodium peroxide are strongly basic and react readily to form highly soluble, strongly alkaline sodium hydroxide. The peroxide also releases oxygen gas, causing effervescence. Magnesium oxide is less basic. It only reacts slightly with water to form a sparingly soluble, weakly alkaline solution of magnesium hydroxide. Meanwhile, aluminum oxide and silicon dioxide have absolutely no reaction with water, owing to their amphoteric and weakly acidic natures, respectively, as well as their strong lattice structures. The non-metal oxides on the right side of the period act as acid anhydrides. When they dissolve in water, they form acidic solutions. Phosphorus 3 oxide yields phosphorus acid, while phosphorus 5 oxide yields phosphoric acid. Sulfur dioxide dissolves to form weak sulfuric acid, but sulfur trioxide reacts violently and exothermically to produce strong sulfuric acid. The various oxides of chlorine react with water to form a range of strong oxyacids, from hypochlorous acid all the way up to perchloric acid. Because basic oxides like sodium and magnesium oxide are already basic, they do not react with strong alkalis like sodium hydroxide. However, our amphoteric aluminium oxide does. It reacts with hot concentrated sodium hydroxide to form soluble aluminate complexes, such as sodium tetrahydroxoaluminate. The acidic oxides also react readily with alkalis. Silicon dioxide forms sodium silicate, sulfur dioxide forms sodium sulfite, and phosphorus pentoxide forms sodium dihydrogen phosphate. These reactions typically happen in 2 stages. The oxide first forms an intermediate acid with the water present, which then neutralizes the alkali. Conversely, when we introduce mineral acids like hydrochloric or sulfuric acid, the basic oxides of sodium and magnesium, along with the amphoteric aluminum oxide, react readily to form their respective salts and water. The reactivity naturally decreases as we move across the period. The strictly acidic oxides of phosphorus, sulfur, and chlorine do not react with acids at all. There is one notable exception. Silicon dioxide will react with aqueous hydrogen fluoride to form a soluble hexafluorosilicate complex ion and water. Now, let's shift our focus from the oxides to the chlorides of period 3 elements. Just like the oxides, we see a clear transition in physical states and bonding. Sodium and magnesium chlorides are solid, giant ionic lattices with high melting and boiling points. As we reach aluminum chloride, the bonding becomes predominantly covalent, and it actually sublimes at a relatively low temperature. From silicon tetrachloride onwards, we are dealing with simple molecular structures that are liquids or gases at room temperature, held together only by weak van der Waals forces. The trend in the melting points of these chlorides is a steady decrease across the period. Sodium and magnesium chlorides require a lot of energy to overcome their strong ionic bonds. But why does aluminium chloride have such an abnormally low melting point? It comes down to polarizing power. The aluminium ion is small and highly charged, giving it a massive charge density. It pulls strongly on the electron cloud of the relatively large chloride ion, distorting it and creating a predominantly covalent bond. This weakens the overall lattice. The nonmetal chlorides have even lower melting points because they rely entirely on weak intermolecular van der Waals forces. Because aluminum chloride is predominantly covalent, it behaves quite differently from typical salts. It can actually dissolve in nonpolar organic solvents. When it does, or when the anhydrous solid is heated and sublimes into a vapor, the molecules undergo association. Two aluminum chloride molecules join together to form a dimer, Al2Cl6. In this structure, two of the chloride atoms act as bridges, forming coordinate bonds with the aluminum atoms to help them achieve a stable octet of electrons. To prepare these anhydrous chlorides in the laboratory, direct combination is often used, simply heating the pure element in a stream of dry chlorine gas. For aluminum chloride specifically, it can be prepared industrially by heating aluminum oxide and carbon in dry chlorine. In the lab, heating aluminum metal with dry hydrogen chloride gas works well. A critical constraint here is that the entire apparatus must be kept strictly anhydrous, often using calcium chloride guard tubes. If any moisture is present, the aluminum chloride will immediately react with it. If we don't need the anhydrous form, hydrated aluminum or magnesium chlorides are easily prepared by reacting the metal, its oxide, or its carbonate with aqueous hydrochloric acid, followed by crystallization. For the nonmetal chlorides, silicon tetrachloride is made by heating silica and carbon in dry chlorine. Phosphorus trichloride is synthesized industrially by reacting chlorine with white phosphorus dissolved in carbon disulfide, continuously removing the product to prevent it from reacting further with chlorine to form phosphorus pentachloride. Disulfur dichloride is obtained by passing dry chlorine over molten sulfur. When we add these chlorides to water, their ionic versus covalent character dictates the outcome. Sodium chloride is highly ionic. It simply dissolves and ionizes completely, leaving a neutral solution. Magnesium chloride, however, undergoes partial hydrolysis. The magnesium ion has a slightly higher charge density, so when it hydrates to form the hexa-aqua magnesium complex ion, it pulls on the water molecules strong enough to release a small amount of hydrogen ions. This partial hydrolysis results in a slightly acyclic solution that will turn blue litmus paper red. Aluminum chloride reacts violently with water. If you add just a few drops of water to the solid, it splutters, releases heat, and produces thick white fumes of hydrogen chloride gas. If dumped into a large volume of water, it dissolves but undergoes extensive cationic hydrolysis. The small, highly charged aluminum ion forms a hexa-aqua complex, aluminum H2O6 3+. Its extreme polarizing power draws electron density away from the attached water molecules, weakening their oxygen-hydrogen bonds and causing them to release protons into the solution. This makes the resulting solution highly acidic. Because this aqueous aluminum chloride solution is so acidic, it exhibits some interesting reactions. Adding sodium hydroxide initially forms a white precipitate of aluminum hydroxide, which then dissolves in excess alkali to form a soluble aluminate complex. Ammonia also forms the white precipitate, but it won't dissolve in excess. If you add a carbonate or bicarbonate, the hydrogen ions in the acidic solution react to release bubbles of carbon dioxide gas, while aluminum hydroxide precipitates out. Even adding magnesium ribbon will cause effervescence as hydrogen gas is displaced by the metal. The covalent nonmetal chlorides react completely and often vigorously with water, a process called complete hydrolysis. Silicon tetrachloride fumes in moist air as it reacts with water vapor to form solid silicon dioxide and hydrogen chloride gas. Phosphorus trichloride and pentachloride hydrolyze to form phosphoric and phosphoric acids, respectively, alongside hydrochloric acid. Sulfur dichloride disproportionates in water to form solid sulfur, sulfur dioxide gas, and hydrochloric acid. Even chlorine gas itself reacts partially with water to form a mixture of hypochlorous and hydrochloric acids. Having thoroughly explored the properties and reactions of period 3 compounds, we can apply this knowledge to industrial processes, specifically the extraction of aluminum. Aluminum is far too reactive to be extracted using carbon reduction, so it is obtained via the electrolysis of molten aluminum oxide. This oxide is sourced from an ore called bauxite, which is essentially hydrated aluminum oxide mixed with significant impurities like silicon dioxide and iron 3 oxide. To get pure aluminum, we must first purify the bauxite through a process called leaching, which we just rush right into the chemical processes used to isolate this vital metal. Let's look at how we prepare pure aluminum compounds from ore, specifically focusing on the purification of bauxite. The first step is roasting the ore. This is crucial because it converts any iron 2 impurities into iron 3 oxide. Next, the roasted ore is heated with concentrated sodium hydroxide. This takes advantage of the different chemical properties of the oxides present. Aluminum oxide is amphoteric, and silicon dioxide is acidic, so both of these dissolve in the strong base to form tetrahydroxoaluminate and silicate ions, respectively. However, iron 3 oxide is a basic oxide. It will not react with or dissolve in the sodium hydroxide, allowing us to easily filter it out as a solid residue. Once the basic insoluble materials are filtered off, we are left with a filtrate containing our dissolved aluminum and silicon compounds. The next goal is to separate the aluminum from the silica. We do this by precipitating aluminum hydroxide while the silica remains dissolved. There are two main ways to achieve this. The first is by bubbling carbon dioxide gas through the solution, which lowers the pH and causes the aluminum hydroxide to crash out as a solid. The second method is called seeding. Seeding is a fascinating process where we add a tiny crystal of pure aluminum hydroxide to the solution. This acts as a nucleation site, inducing the tetrahydroxoaluminate ions to hydrolyze and precipitate out as a large mass of solid aluminum hydroxide. After we have successfully precipitated the aluminum hydroxide, we need to convert it back into an oxide form that is suitable for electrolysis. The solid aluminum hydroxide is filtered, washed to remove any remaining impurities, and then subjected to intense heat. This thermal decomposition process is called calcination. As you can see in the equation, heating the aluminum hydroxide drives off water vapor, leaving behind pure, concentrated aluminum oxide, commonly known as alumina. This pure alumina is the starting material for the next major stage, extraction. To extract pure aluminum metal from the alumina, we use electrolysis in a process known as the Hall-Héroult process. Here is a diagram of the electrolytic cell. Notice the steel tank lined with refractory bricks and an inner lining of graphite, which acts as the cathode. Suspended from copper clamps into the tank are large graphite blocks acting as the anodes. The electrolyte is a solution of our purified aluminum oxide dissolved in molten cryolite. Pure aluminum oxide melts at over 2000 degrees Celsius, which is incredibly expensive to maintain. By dissolving it in cryolite, the melting point of the mixture drops to around 900 degrees Celsius, saving massive amounts of energy. The cryolite also acts as an excellent solvent and improves the electrical conductivity of the cell. Let's break down the chemistry happening at the electrodes, starting with the cathode. The graphite lining of the tank serves as the negative electrode. Here, the positively charged aluminum ions in the molten mixture are attracted to the cathode. They undergo reduction, meaning each aluminum ion gains 3 electrons to form neutral, liquid aluminum metal. Because this molten aluminum is denser than the cryolite aluminum mixture, it sinks and collects at the bottom of the cell. From there, it can be conveniently tapped off periodically through an outlet without interrupting the continuous electrolysis process. Meanwhile, at the positive anodes, oxidation is taking place. Oxide ions lose electrons to form oxygen gas. However, this creates a significant engineering challenge. The anodes are made of carbon graphite, and the cell is operating at 900 degrees Celsius. At this high temperature, the freshly generated oxygen gas reacts immediately with the carbon anodes, producing carbon dioxide gas. Consequently, the anodes literally burn away over time and must be continuously lowered into the melt and eventually replaced. Additionally, the process is run at a relatively low voltage. This is a deliberate choice to ensure that only the aluminum oxide is decomposed, preventing the breakdown of the valuable cryolite solvent. Aluminum is an incredibly versatile material due to its unique physical properties. It is a silvery white metal that is notably lightweight, soft, and highly malleable, meaning it can be easily shaped or rolled into thin sheets. Because of its low density and high strength-to-weight ratio when alloyed, it is a primary material in the transportation industry, used in everything from aircraft and spacecraft to everyday automobiles and bicycles. Furthermore, aluminum naturally forms a thin protective oxide layer on its surface, making it highly resistant to corrosion. This property makes it ideal for packaging, such as foil, and for food and beverage containers, ensuring the contents remain uncontaminated. In analytical chemistry, we use specific tests to identify the presence of aluminum ions in a solution. The most common test involves adding sodium hydroxide. When you add sodium hydroxide dropwise to a solution containing aluminum ions, you will first observe the formation of a white precipitate. This is insoluble aluminum hydroxide. However, the defining characteristic of aluminum is its amphoteric nature. If you continue to add sodium hydroxide until it is in excess, that white precipitate will dissolve, leaving a clear, colorless solution. This happens because the aluminum hydroxide reacts with the excess hydroxide ions to form a soluble complex ion, tetrahydroxoaluminate. Another critical test uses aqueous ammonia. Similar to the sodium hydroxide test, adding ammonia dropwise provides hydroxide ions, resulting in the same white precipitate of aluminum hydroxide. But here is the key difference. When you add excess ammonia, the precipitate does not dissolve. It remains insoluble. This allows us to distinguish aluminum from other metal ions like zinc, which would dissolve in excess ammonia. Furthermore, this precipitation occurs even if ammonium chloride is present in the solution. It's worth noting that aluminum, chromium, and iron-3 hydroxides all share this behavior of precipitating with ammonia, regardless of the presence of ammonium chloride. Because the aluminum ion has a high charge density, it strongly polarizes water molecules in solution, making aqueous aluminum solutions quite acidic. We can see evidence of this acidity in two specific tests. If you add drops of sodium carbonate or sodium hydrogen carbonate to an aluminum solution, you won't just get a white precipitate of aluminum hydroxide, you will also see bubbles of a colorless gas. This gas is carbon dioxide, generated by the acidic solution reacting with the carbonate. Similarly, if you drop a piece of magnesium metal into the solution, you will observe a white precipitate and effervescence. In this case, the gas is hydrogen, produced as the magnesium reacts with the acidic environment. Continuing with our qualitative analysis, if you bubble hydrogen sulfide gas through an aluminum solution in the presence of ammonia and ammonium chloride, you might expect a sulfide to form. However, you actually get a white precipitate of aluminum hydroxide. This occurs because any aluminum sulfide that tries to form is immediately hydrolyzed by water back into the hydroxide. Another visually striking test is the litmus lake test. You add dilute hydrochloric acid and a few drops of litmus solution, then add ammonia until the mixture is alkaline. As the aluminum hydroxide precipitates out of the alkaline solution, it physically absorbs the blue litmus dye, creating a suspended blue solid known as a lake. To absolutely confirm the presence of aluminum, we have a few more specialized tests. Adding disodium hydrogen phosphate yields a distinct white gelatinous precipitate of aluminum phosphate. If you use alizarin solution followed by ammonia, the aluminum hydroxide precipitate will absorb the alizarin dye, forming a characteristic pink lake. Finally, there is a dry flame test using cobalt-2 nitrate. You mix the sample with a drop of cobalt nitrate, soak it onto filter paper, and heat it strongly directly in a flame. If aluminum is present, it will react to form a bright blue ash, which is a compound called cobalt-2 aluminate. This is a very definitive confirmatory test. Let's apply our knowledge to a practical scenario. A student notices that aluminum chloride behaves like a covalent compound, while aluminum oxide behaves like an ionic one. Why does this happen if they both contain aluminum? The answer lies in Fijon's rules and polarization. The aluminum ion has a high 3+ charge and a small radius, giving it a very high charge density. The chloride ion is quite large, meaning its outer electrons are loosely held. The highly charged aluminum ion distorts or polarizes the chloride's electron cloud, pulling those electrons into the space between them and creating a covalent bond. In contrast, the oxide ion is much smaller and holds its electrons tightly. It resists this polarization, so aluminum oxide remains predominantly ionic. The student also wonders why aluminum fluoride has a dramatically higher melting point than aluminum chloride. Building on our previous explanation, fluoride is a very small, highly electronegative ion. It completely resists polarization by the aluminum ion. As a result, aluminum fluoride forms a massive, continuous, giant ionic lattice. Melting it requires breaking incredibly strong electrostatic bonds, which takes a lot of heat energy. Aluminum chloride, however, is covalent. It exists as discrete simple molecules, specifically dimers of Al2Cl6. To melt or boil aluminum chloride, you only need to overcome the weak van der Waals forces between these molecules, not the covalent bonds themselves, resulting in a very low melting point. In fact, it usually sublimes. In our second scenario, we investigate the periodic trends of period 3 elements reacting with oxygen and water. As we move across the period from sodium to chlorine, the nature of the oxides changes dramatically from basic to amphoteric to highly acidic. Sodium oxide and magnesium oxide react with water to form hydroxide solutions, resulting in a pH greater than 7. Aluminum oxide and silicon dioxide are giant structures that are insoluble in water, so they don't affect the pH of the water they are placed in. However, the nonmetal oxides on the right, phosphorus, sulfur, and chlorine oxides, react vigorously with water to form strong acids like phosphoric, sulfuric, and perchloric acid, resulting in a pH well below 7.
We see a similar trend with the period 3 chlorides. On the far left, sodium chloride is a simple ionic salt that dissolves in water without reacting, leaving a neutral pH of 7. Magnesium chloride dissolves but undergoes very slight hydrolysis, making the solution just barely acidic. But starting with aluminum chloride, the covalent character takes over. Aluminum chloride, silicon tetrachloride, and phosphorus pentachloride do not just dissolve, they react violently with water in a process called hydrolysis. As you can see in the equations, these reactions produce hydrogen chloride gas, which dissolves to form hydrochloric acid, driving the pH of the resulting solutions significantly below 7.
And that brings us to the end of our comprehensive look at aluminum. To wrap up, remember that the Bayer process relies on the amphoteric nature of aluminum to purify the ore, while the Haller-Rolt process uses electrolysis and cryolite to efficiently extract the metal. We saw how this amphoteric behavior is also the basis for identifying aluminum ions in the lab using sodium hydroxide and ammonia. We applied Fajon's rules to understand why aluminum chloride is covalent despite being a metal-nonmetal compound. Finally, we placed aluminum in its proper context within period 3, observing how chemical properties shift from basic and ionic to acidic and covalent across the periodic table. Keep these core principles in mind, and you'll master the chemistry of aluminum.